Thank you, Jerome, and thanks to the organizer. I'm really happy to be here because I'm going to talk about a work that took a lot of time, like let's say a couple of years. It was more a journey than a work. It's in collaboration with Maciek that is here, with Jacopo that will arrive, and also Milos. I think he will arrive. Part of the result I also shared with Friedrich and Benjamin. I mean, mostly in the beginning of the talk, and they're based on 2 projects that we have made recently. So the basics of this project is the dynamic of integrable models, and fortunately we got a very good introduction this morning from Herbert. So I will go pretty fast. So integrable model, they have an infinite number of conserved charges that are local or quasi-local, so we can express them as a density of charges. And at equilibrium, they are described by GGs that have an infinite number of inverse temperature. We are going to study them out of equilibrium using hydrodynamic assumption. So we are going to assume smooth state and long times. In this way, all the inside all the fluid cells, the system have time to relax, and we're going to describe the state of the system using local entropy maximization. So the state of the system locally will be described by some local temperature. This is nice because in this way we can not only write local state but also express the dynamics using dynamic projection. So in this way we assume that all the fast degrees of freedom have already relaxed, and that the dynamics is simply given by the dynamics of the slow modes, that in this case are the density of quasi-particles. The good thing about integrable models is that in most of the case we can express them in terms of quasi-particles that are a bit more physical, at least in our sense. And so as also Herbert told this morning, at Euler scale, this gives a very simple equation. In fact, in terms of quasi-particle, we have simply a ballistic propagation given by an effective velocity that is taking into account also the interaction with the background. For example, here we have an hard-sphere gas that is integrable and it's very simple. It's a classical system. And you can see that averaging over some interaction, the dynamics is not given by the bare velocity, that is the dashed line, but is given by the effective velocity, that is the solid one. Then there are higher order effects. This is also nice because we can include some integrability breaking term into it under the assumption that these integrability breaking term are sufficiently smooth, in the sense that inside each fluid cell, the system still looks like integrable, and the integrability breaking only looks like an acceleration of these charges between the fluid cells. This is pretty useful because we can describe physical situation like the one in a Kinoshita experiment where they had cold atoms loading into a harmonic trap, or many other experiments. And what we are usually interested in is in out of equilibrium situation where we initially quench the system from an equilibrium state, changing the Hamiltonian, switching on, for example, this term, and then look how the system relaxes to the thermal state, the real thermal state. So what's the main motivation of this work? Is another experiment that was performed in 2018 in the group of Benjamin Lev. Also, Marcos Rigol and Sarang will be here, I think, next week. I don't know. In this experiment, they they measured the evolution of an ultra-cold bosonic dysprosium atoms system. And in this case, the system was loaded into a quasi-one-dimensional array of potential. These dysprosium atoms have the property of having a very strong magnetic dipole-dipole interaction. So effectively, they are interacting with this large-scale potential. So they are not only interacting inside the same tube, but they're also interacting between different tubes. How they describe this system is by considering separately the interaction inside the same tube and between different them. To describe the interaction inside the same tube, what you have to do is to integrate the equation of motion, the Schrödinger equation in the other direction. And this way you get an interaction that has a large-scale component that is decaying as the cube of the distance and a delta function. What they do is to consider the peak of this function as a correction to the delta peak, and in particular, this delta peak is an integrable interaction typical of Linear model, and then to consider the rest as an integrability breaking perturbation. And then on top of that, we also have the intertube large-scale interaction that is coupling different tubes. So this is effectively an integrability breaking setup where we have Linear, and on top of that, we have a large-scale integrability breaking. What they observe is that there is a thermalization of the system at large temperature. In fact, the system is relaxing to something that is close to Gaussian. And the thermalization rate is proportional to the total integrability breaking term squared, and is also proportional to the integrable interaction squared. A theory that is describing this experiment it was still not developed, so we accepted the challenge. And in this case, what we want to do is to develop a dynamic theory that is describing the large-scale evolution of a gas that is evolving under an Hamiltonian that has an integrable interaction, and on top of that, a two-body interaction that couple the density. The main assumption that we are doing is that this interaction is characterized by an interaction length that is sufficiently large, meaning that this is coupling different fluid cells. And this psi will be also our dynamic length. So we have two parameters, V0 that is the parameter, the strength of the potential, and then psi that is controlling the length. So if you have, instead of integrable Hamiltonian and on top a perturbation, you have a free Hamiltonian and on top a perturbation. In classical system, if you want to study the evolution of density and of correlation, the generic theory is the BBGKY hierarchy. So if you write the density of particles, the microscopic density of particles, and then you compute average, what you find is a hierarchy of equation where the density of particle is depending on the two-point function, and where the two-point function is depending on the three-point function, and so on. In order to solve this set of equations, you need to define a truncation scheme, and the most famous one is this cluster expansion or Born approximation, where you just discard the endpoint connected function, assuming that they are scaling with the potential. So something very interesting is happening indeed in one dimension. In fact, if you simply take these two sets of equations in 1D for classical system and you try to solve them, what you find is that these two equations are not thermalizing. Physically, this is coming because a simple scattering between an elastic scattering between two particles in 1D is not relaxing the momenta, while in higher dimension, this is happening due to the complexity introduced by the angle in the scattering. So the thermalization in 1D requires three-body scattering, and the information about them are in three-point function. The phenomenological result of this is that the thermalization timescales are extremely long. So for classical system, in this case, they are scaling with the fourth power of the interaction potential. And also, if you try to find some kinetic equation only integrating these two, you will find that in 1D, all of them are vanishing because of this. So we are ready to generalize this result, also including integrable interaction. So we are merging together many stuff. We have integrability, hydrodynamics, BBGKY, and we found reasonable to call it generalized BBGKY or GBBGKY. So first of all, since we are assuming local entropy maximization, we need to define over which local state we are computing the charge densities. In this case, this is a bit unusual, but we are extending the usual local GG, including also higher correction. This is somehow an extension of what was already done in this other paper. And this is simply to include the presence of long-range correlation in the system. And in this case, these generalized inverse temperature that are coupling the different points are simply proportional to the endpoint correlation function. And this will be the fundamental field of the theory. So we're going to find the equation to describe the evolution of these objects. So then the first step is just to look at how density of charges evolve. We take the commutator with the Hamiltonian. We find that we have a current that is coming from the integrable Hamiltonian, and then an interaction term where these J I0 are nothing else than generalized currents coming from the commutator with other charges. And then in order to build the hierarchy, we simply multiply different charge densities, and then we take local average. In this way, we can find the hierarchy. While doing this, of course, you find average of currents and average of product of current with charges. We need to deal with them. Again, we are going to use a dynamic projection, inspired somehow by, again, by this other work, not only taking the linear term, so the Euler contribution, but also the diffusive scale one that is involving higher point function. So also the dynamic projection has a kind of a hierarchical structure. And crucially, in this kind of object, so for the 2-point function, this is involving 3-point function. So now that we have this, okay, these are kind of technical steps, because while you have to, when you average product of quantities, you also find some delta function contribution, and this object can be computed exactly using the state assumption that I gave before. And now we can define the truncation scheme that is really inspired by BBGKY. And in this case, we have 2 parameters that are the psi, the dynamic length, and also the potential parameter V. When you look at this object, you can find that using both the ordering and the typical large deviation scaling, the 2-point function is scaling like 1 over L, with the contribution being proportional to the potential, and 3-point function 1 over L squared, with the also contribution proportional to the potential. When you put all this stuff together and you look at what is dominant and what is subleading, you get all these equations that are the first 3 layers truncated at leading terms. They're very complicated, but I'm gonna try to give some intuition. First of all, this is the only for homogeneous system. In this case, the 1-point function doesn't have any ballistic propagation because the system is homogeneous. It's only evolving slowly due to the interaction given by the connected 2-point function. Then the evolution of 2-point function have on left-hand side 2 contributions. The Euler scale propagation, so the ballistic propagation, and then on top of that, a diffusive scale propagation that is depending on this 3-point function. And on the right-hand side, we have the interaction that is driving the 2-point function, and the leading term is nothing else than the mean field contribution. Finally, for 3-point function, in this case, we find something that is different than what is happening for free system. In fact, here we have a ballistic propagation that is slightly more complicated, but this is just coming from a dynamic projection. And then on the right-hand side, as the driving term is purely integrable and is coming simply from the creation of two-point function. This is also something that can be found using BMFT. And these three set of equations that can be then integrated in order to find a kinetic equation only for the one-point function. It's a bit tedious and long calculation, but you can do it. And once you do it, you can find, in terms of quasi-particle, simply an equation for the density of rapidity with a scattering integral that is satisfying the H theorem, so is increasing entropy and is stationary in the thermal state and is conserving energy, momentum, and number of particles. If you look at the parameter in front of this, you can find that the thermalization timescale is proportional to the perturbation squared and the integrable interaction squared. And this is nice because this is the same parameter that they found in the experiment. Also numerically, if you consider, for example, a hardened gas, you see that at large time, you can find a good collapse using this scaling. Now, this hierarchy is not only useful to derive a kinetic equation, but you can also really solve the hierarchy. This is what we did here. So again, we are considering this hardened gas with this potential that is letting rods interacting. And here we are looking at the kurtosis of the rapidity distribution of particle distribution. Here the dots are the numerical data, while the solid line is the BBGKY. How we did it is to solve only the first two equations of the hierarchy until an intermediate time, and at large time we just solved the kinetic equation. And what we find is that we have a really good prediction for the evolution of this gas. Also, since this is kurtosis and at thermal state this is 0, we see that the system is thermalizing exponentially in time, since this is a log plot. And this is also a kind of a two-stage process. In fact, if you look at kinetic energy, you see that there is a fast evolution, and then you reach a state where the kinetic energy is conserved. And the stage where kinetic energy is conserved is the stage where the Boltzmann equation is predicting. So this is not only giving the evolution of one-point function, this is also giving evolution of correlation. So for example, here we have a correlation of density-density correlation, momentum, and energy. And we can see that the theory is predicting very well the non-trivial creation of this long-range correlation. So then we wanted to check this against some other analytical method. And something is doable. In fact, if you have a macroscopic theorem system, you can write the BBGKY, truncate it, find some Landau equation that is the kinetic equation that we derived. And actually, this is in the grazing collision limit equal to the Boltzmann equation. Grazing collision limit is nothing else than the limit where the difference of outgoing moment after each scattering is small, so the small momentum limit. And the Boltzmann equation for a certain model can be derived from Fermi-Golden rule. Explicitly for Lieb-Liniger model, for example, you can derive the Boltzmann equation just by using this form factor expansion. And if you perform this calculation for Lieb-Liniger, you find that this Boltzmann scattering integral is really complicated, but is still computable. It's depending on the scattering shift of the integrable model. It's depending on the difference of many difference of effective velocities, the Fourier transform of the interaction potential, and explicitly is proportional to the cube of the density. And actually, this very complicated scattering integral is matching term by term with the scattering integral that we derived using the BBGKY. And these two derivations are completely independent. So it's a very strong check for our hierarchy. So now that we have a theory and we tested it against a simple model like Harders, we want to do something more and want to check how this is performing with comparing it with the experimental results. So again, we are still motivated by the dipolar quantum Newton kernel I told you before. We are considering a Lieb-Lineker model that is perturbed by this dipole-dipole interaction. We are both considering the interaction inside the same tube and interaction between different tubes. So as I told you before, the interaction inside the same tube can be computed integrating the Schrödinger equation over the transfer direction. If you do this, you can find that the effective dipole-dipole interaction inside the same tube has a typical length scale that is given by the typical length scale of the trapping potential. And if you compare it with the effective hardcore interaction given by the van der Waals repulsion for these bosons, you find that this is smaller. So what we did differently from the experiment is to consider the interaction inside the single tube just as a normalization of the Lieb-Lineker coefficient. So inside the single tube, the dynamics is entirely integrable, and is also confirmed by some more recent result of the same group. And we are considering as a unique integrability breaking contribution the interaction with other tubes. Now, this model is pretty complicated, so we have to do some approximation. First of all, we considered only nearest neighbor tubes, so the first four in this lattice. And then we also consider the same state in each tube. Then we can generalize this hierarchy, including many tubes, just by inserting another index that is telling which tube is which and adding a summation over the interaction between different tubes. And finally, the only thing that we had to fit was the initial state that didn't have any analytical prediction. And since we were at high temperature, what we did is to take the quasi-particle density from the measured momentum density. This is not exact, but at high temperature is expected to be a good approximation. And just by fitting this and making the other approximation, we could compute the thermalization timescale by looking at the difference of the state with respect to a Gaussian, that is the thermal state expected at a temperature. And from this, we could extract the thermalization timescale. And if you compare this with the experimental result, just by fitting the initial state, we can find that the comparison is pretty good. Is not perfect, mainly due to the approximation we made before. So this is kind of the end of the story. No, this is not the end of the story. There is something else we're working on. In fact, we are recently asking if the Boltzmann equation is always valid. I mean, if this is sufficient to describe the whole internalization process. So what we did is to take again our system. We decreased a little bit the interaction length in order to have thermalization at a smaller time. And at this point, we're looking if this was matching with an exponential decay. This was working until we reach longer term. At this point, what we found is that along the time power low tail is appearing. This clearly an effect that is connected to hydrodynamics. And what we're asking now is the kurtosis of the density of the distribution of velocity. So it's going to zero at thermal state. And yeah, so this is like an open question, and we're working on this, and we would like to connect this behavior to the BBGKY hierarchy, understand how to go from the BBGKY hierarchy to this hydrodynamic regime, and would like to talk about this if someone is interested. Thank you.
All right. Thank you.
I have one, I mean, it's a slightly general question. I mean, so when you look at ideal gas, you know, I mean, standard kinetic theory and then at the corresponding kinetic equation, then you have two options. I mean, you have sort of like in hard spheres, you know, when at the collision, I mean, you have a sort of, you know, big change, but you do it very rarely. So, you know, you have a very dilute gas and then you sort of have whatever, you know, these collisions, and then you get the Boltzmann transport equation. And on the other side, I mean, you could imagine that we have an interaction which is sort of weak, and then you actually, your gas has sort of like a finite density, and then you get the Landau equation. And it's I just wonder whether in your case, I mean, you sort of seem to say that in your context, I mean, it's always the Landau version which sort of is useful, or yeah, that's somehow the question.
I mean, it depends a bit on the regime you are interested in. In our regime, we are not imposing any low density in the state. What we are always considering is small like weak interactions. What we used is that these two approximation, they match if you use this limit. So in this case, we use this kind of Landau approach because it's. I mean, in this case, we were interested in this because if you have the BBGKY hierarchy, then you can also have the dynamics of correlation, not only the kinetic theory. So you have more information.
Yes.
Yeah, so I mean, so it seems like in your eventually it goes to the Gibbs state. Is that right?
Yeah.
And so it happens quite fast, like exponentially. Right. That's what the time you said it.
Yeah. I mean, it's true. It goes down exponentially, but yeah, it's not very fast because the coefficient in front of the exponential is suppressed with the interaction length and with the strength of the potential, both of them squared. So it's I mean, it's exponential, but the coefficient in front of it it's a bit small.
Oh, so actually it's a very slow relaxation.
Yeah, so it's a very slow relaxation.
Because otherwise, I mean, if it was like, okay, maybe if the interactions are strong enough, then one can just use normal hydrodynamics, right? One wouldn't need this like.
Yeah. What you have is that the this crossover. What I expect is the parameter, like the time of this crossover is going closer to zero when you have a strong interaction. So the full dynamics is described by hydrodynamics. This
Some other questions? So I have one. So I mean, many results are for the classical hard-order gas, right? To what extent should we believe that this carries over to quantum case?
What do you mean?
Well, your initial motivation was a quantum model, no?
Yeah.
So should we just believe that that's the same thing?
Well, we have, I mean, we already have some, something to let you think that, yes. One confirmation comes from the comparison with the Fermi-Golden rule approach coming from the Lieb linear. So in this case, we find that the Boltzmann scattering integral is really matching with the Landau equation that we computed. And also we compared with the quantum system, and we got like a fairly good result. So
the quantum system is directly the experiment.
Yeah, like the red dots are the experimental dots. So I would say yes. What is, I mean, if you have integrable quantum spin chain, could be different, I would say. But for quantum system, integrable quantum system in the continuum with the perturbation, I think gives a good prediction.
Okay. Other questions? So no. Okay. So let's thank Leonardo again.